And now we come to the fundamental idea behind statistical mechanics, the idea of equipartition. Here's the idea. You've got atoms, and they can do different things. They can have the energy in the form of motion in this direction, or the motion in that direction. If it's a diatomic atom, it can be vibrating back and forth, or it can be rotating around different axes, around this, or whatever. So the energy can be in all these different forms: motion, different directions; vibration, different directions; spinning, different directions. Well, the principle of equipartition says that on average they will all have the same amount of energy, and that energy in every possible state will be half kT, where K is Boltzmann's constant. And T is a temperature in Kelvin. Deceptively simple, but let's think about it a bit. So what it's saying is that, let's say you had a whole bunch of molecules and they were all moving back and forth along a given direction. But the situation wouldn't last. Before long they'd bounce off each other, ricochet off, and they'd bounce in different directions, and before long they'd all be colliding, and so they'd have their motion spread over all directions. So you'd expect about the same amount of energy on average in each of the x, y, and z coordinates. Likewise, let's imagine you had a lot of diatomic molecules, and they weren't rotating, they were just moving along. But if they bang into other ones, just imagine them hitting here, that's going to get them both spinning. So, even if you started with the diatomic molecules not spinning, all the energy in the form of motion, before long the collisions are going to get them spinning. And if you get two spinning things bashing into a stationary one, that'll probably get that one moving. So once again, you'd expect on average that the rotation energy, and indeed the vibration and the linear motion, will all have the same amount of energy if you're in a situation where there are lots and lots and lots of collisions between these things going on all the time. So that's the basic idea. So equipartition says all these different states will on average have the same amount of energy. Any particular atom or molecule at a particular time will probably have more energy in one state, say rotation or vibration, than some other, but on average over all of them, they should be the same. How about this equation? Well, that's actually just a definition of temperature. We've decided that temperature is a measure of the amount of energy of all the microstates. I should mention that these are called microstates. Moving back and forth this way is one microstate, moving up and down is another microstate. So equipartition says every microstate has the same energy, and that energy is given by this. I suppose you could have had E proportional to T squared or some other thing like that. And if you want, you can define temperature that way. It's not how we normally define it, but it turns out that a linear relationship, E proportional to temperature, seems to work best, most simply. And for historical reasons, the constant is half a K.